In this video, we are going to focus on evaluating logarithmic expressions. You just learned how to rewrite an exponential equation as a logarithmic equation and a logarithmic equation as an exponential equation. So today, we are going to use that strategy of switching one form into the other. So to start, instead of looking at this as an expression, I am going to rewrite that log base 4 of 16 equal to x. Because that's what I'm trying to do. I'm trying to figure out what that expression equals. Now, I'm going to switch that to an exponential equation. So remember, this is equivalent to 4 raised to the x equals 16. The base of the log is the base of the exponential expression, and that exponent for my exponential expression is always what that log equals. So now you're asking yourself, 4 to the what equals 16? Well, we all know that it's going to be 4 squared. So that means that log base 4 of 16 is equal to 2. Let's look at number 2 using the same strategy. I'm going to take that expression, log base 5 of 125, and I'm going to set that equal to x. Again, my goal is to figure out 5 to the what power equals 125. So let's change this to an exponential equation. 5 to what value or what power equals 125? 5 to the x equals 125. Well, I know that 5 cubed is 125. So that means the value of this expression, log base 5 of 125, is going to be 3. Let's try this again. I'm going to set this expression, log base 1/3 of 81 equal to x. So now it's saying 1/3 to what power is going to give me 81? Let's look at that as an exponential equation. 1/3 to what power equals 81? Now, that's a little bit more challenging. If the 3 is in the denominator of the fraction, I need to figure out some way to bring it to the numerator. And in order to do that, I'm actually going to make that x value a negative number. Well, I know that 3 squared is 9. I know that 3 cubed is 27. And I also know that 3 to the 4th equals 81. Well, here's that 81. So what I'm thinking is, for me to get that 3 out of the denominator, I need to take its reciprocal. And I know if I raise a ratio to a negative exponent, it's going to take the reciprocal of that fraction. So if I raise that 1/3 to a negative exponent, it's going to put that 3 in the numerator. And if I choose to make that a negative 4, not only is it going to take the reciprocal of that 1/3, making it 3, this is going to be equivalent to 3 to the 4th, and that is 81. We already saw that here. So that means the answer to my equation, 1/3 raised to the x equals 81, is going to be negative 4. So that means this expression, log base 1/3 of 81, is going to be equal to a negative 4. So 1/3 raised to the negative 4th power is 81. Okay, one more example. Same strategy. I'm going to set that log base 2 of 64 equal to a variable equal to x. I'm going to interchange those or switch those forms. So now that's the same thing as 2 raised to the x power equals 64. So 2 to the what value gives you 64? Well, I know that's going to be a 6. So that means that log base 2 of 64 equals 6, because what that's actually asking me for is 2 to the what power gives me 64. 2 to the what power gives me 64. In this next section, we are going to focus on evaluating expressions using a calculator. So please grab a graphing calculator And I'm going to show you two different methods on how to do this. We're going to start by pushing the math key on our calculator. So on your graphing calculator, that was the third one down on the left. Now, if you push that math key, underneath it, if you go down to A, you could actually arrow up. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it has A. And next to it is a lowercase log and a capital base. And then there's a little parenthesis. Well, if you push enter, it is going to look like log. And then there's a little box here, which is actually where my cursor is blinking. And then there's a little box in parentheses. Now, what goes in those spaces? In this spot, that is going to be our base. And in this position, that is going to be our argument. So if you use your calculator, you can put the 2 in the base position. You arrow to the right. You put 5 in the argument position. And then when you push enter, I ended up with the value of that expression, log base 2 of 5, equaling 2, and I'm going to put approximately because I'm going to round this decimal. So 2.3, let's say 219. I'm going to round it to 4 decimal places. Let's try the same thing with number 6. Again, I'm going to push my math key or math button. I'm going to arrow down or arrow up to A with the semicolon. If I push enter, again, it looks like the same notation as it did for the other one. So when I plug my values in there, I'm going to push or enter 7 for where the base is and 190 for where the argument is. Hopefully you're trying this with me. I ended up with that being approximately 2.6964. All right, now not all graphing calculators have that log base application or log base option. So if your calculator does not do that, we are going to use what is called the change of base rule. Now, even if you do not need this, the change of base rule, it is still going to be a very useful formula for you to use when we start solving logarithmic equations. And it looks like this. If I have, let's say, log base b of a, and I'm trying to put that in my calculator. So, for example, that log base 2 of 5, I can change the base to log base 10 of a and log base 10 of b. So what did I do? I took the log of the argument and I divided it by the log of the base. Now, why did I choose to use base 10? Well, that's a great question. If we look on our calculator in that left-hand column, you are going to see a button that is written as LOG, capital LOG. And capital LOG is actually called the common log. And that is when you're working with log base 10. So that is one option that we can use when we're evaluating expressions. The second option we could use is ln. Right below that log is ln, capital L, capital N. And that stands for a natural log. And a natural log is log base E. More of that to come. Super exciting. We'll talk about that in a couple days. So I could use base 10. I could also do ln, which would be log base E. Some people like to use the ln or the natural log. Other students feel more comfortable writing it with base E. But again, what you're doing is you're taking the log of the argument, and my argument was my A, and dividing it by the log of my base. So if we try to do that with this equation or expression up here, log base 7 of 190, let's say I choose to do log base 10. It's going to give you the same value regardless of the base that you choose. You would type that in as log base 10 of 190, and you're going to divide it by log base 10 of 7. Now, some calculators may require you to put parentheses around each expression. Sometimes with that division, you might just need to put a parenthesis around that bottom log, but play around with that a little bit. We all know that our answer is supposed to end up being approximately 2.6964. Now we're going to move on and look at some of the properties of logarithms. Now, we know that exponential equations and logarithmic equations are inverses of each other. And because of that, they have some similar properties. So by definition, the product of, and I'm using x as a base, because why not? Log base x of the product AB is equal to log base x of A plus log base x of B. So you're given each of those terms in the argument their own base. So if you are multiplying values in the argument, then you're adding the logs. And that is similar to what you see in an exponential expression. In an exponential expression, when you're multiplying the bases, let's just say I use x squared and x to the fourth, what are you doing? You are adding those exponents. So when you have a product of arguments, you're adding the logs. All right, let's look at a quotient. So when you're focusing on log expression that has a quotient in the argument, well, each one of those values is going to get its own log again, but you're going to write it as log base x of A minus log base x of B. Now you see that same relationship when you're working with exponential expressions. If you say, for example, x to the 7th over x to the 5th, if you are dividing those bases, then you subtract the exponent. 7 minus 5 would equal 2. So when you are looking at a quotient in the argument, we subtracted the two logs. And when you're looking at a quotient or division, when you are focusing with log expressions or exponential expressions, you subtract the exponents. Okay, we have one more. Now, this is slightly different. Here I have log base b of x, and I have a value or a variable that's in that exponential spot. Well, you never want the argument to have a power. So I'm going to take that exponent and I'm going to put it in the front as a coefficient. So that means that log base b of a raised to the x is equivalent or equal to x times log base b of a. So if you have an exponent for the argument, you can move it to the front as a coefficient. So let's apply these properties. In this first set, we are going to focus on condensing a sum and difference of log expressions. So I'm going to try to write the log of x plus log of y as a single log. Now, if there's no base given, these are going to be referred to as common logs. So that is the same thing as if you saw log base 10 of x plus log base 10 of y. Now, if you're more comfortable writing the base, feel free. If not, then you don't need to do that. You can keep it just as a log. So I want to write this as log base 10, and I'm going to build up this argument. So what I'm looking at when I follow these properties up here, if I am adding two logs, working backwards to build up this argument, that is the same thing as writing that x and y as a product. So we're applying this product property. When you had two expressions in the argument, I gave each one of those terms its own log, and I added the logs together. Now I'm going backwards. Log base 10 of x plus log base 10 of y. I can write that as a single log by combining those arguments and writing it as a product. All right, let's look at the next example. Each one of these have a log base 4. So I know when I write this as a single log, it is going to be log base 4. How do I combine those 4 logs into a single log? Well, what I know is that I'm always going to start with that first argument. So I'm going to start with a 3. Now, the next log is added. So if log base 4 of y is added to that first log, that y is going to be in the numerator because that is going to make a product. The following log, the negative or subtracting that log base 4 of w, since it's subtracting, I'm looking at that quotient property, and the quotient property says that if logs are subtracted, the argument values are divided. So I'm going to place that w in the bottom, so in the denominator. My last term is addition. So now I'm adding log base 4 of z. So since I'm adding, that goes back to multiplication. So the arguments here are multiplied. So let me talk through that again. You always build off that first argument. So 3 went in the numerator. It was adding log base 4 of y. So that y went in the numerator as well, because when you add 2 logs, that's going to be a product in the argument. When you're subtracting your next log, that is going to create a quotient. So the w goes in the denominator, and then you have another sum, which puts that z in the numerator for that argument. All right, problem number 3. This focuses, first of all, on using that power property. So before I start writing that set of 2 expressions or that difference as a single log, I need to make sure that each coefficient is 1. So I'm going to take this 2 and bring it up as an exponent, and the 5 and bring it up as an exponent. So I'm going to write this as log of m to the second minus log of n to the fifth. Now again, there was no base written. If you are more comfortable writing that with a base 10, that's log base 10 of m squared minus log base 10 of n to the fifth. So writing that as a single log, log base 10, always starting off with that first argument. I subtracted my second log, and since subtraction gives me a quotient, that n to the fifth is going to go in the denominator. Last example, a combination of the first 3. Step 1, let's use that product or that power property. The power property is telling us to take all the coefficients and move them up to exponents. So that gives me log base or log of x raised to the 1/4 minus log of y raised to the second minus log of z raised to the fifth. Again, that's a log base 10. In this problem, I'm not going to write it. I'm just going to keep it as a log. I'm going to start off with that first argument, and it's going to go in the numerator. The second log was subtracted from the first, so that means that that y squared is going to go in the denominator. Now, the next log is subtracted as well, so that's going to put that z to the fifth in the denominator because you're always focusing off of how it builds off that first term. We're going to do the opposite for this section. Now we're going to expand. So you're given a single log, and your job is to write it as a sum or difference of logs. So let's quickly go through these properties. When I have a product for the argument and I expand it, each one of those gets their own log, and those logs are added together. When I have a quotient as an argument, each of those values again gets their own log, but those logs are subtracted. Same thing, if you have any sort of exponent to the argument, it needs to move in front as a coefficient. Now, if I'm going to expand, I'm going to basically be looking at the right side of these properties. I'm given a product here, and I'm going to expand it. I'm given both a product and a quotient here. Again, I have to expand. Similar, a product, and again, a quotient. So what I look at to start is how many values I have in the argument. Well, for this first one, I have x, y, and z. That is 3 values. They are multiplied together, so each one is going to get its own log. No base was written, so again, that's log base 10. You could write it in if you choose. I'm going to leave it without. Starting with the first log, which was x, the y was multiplied by that, so I'm going to add the next log. And again, the z was multiplied, so I'm going to add this log as well. So that's log base 10 of x plus log base 10 of y plus log base 10 of z. All right, number 6, I have a quotient. However, when I start, I'm recognizing that there actually is 3 terms in the argument, a 4, an x, and a y. And each one of those needs to get its own log. I'm going to start with the 4. Now, the x is multiplied by the 4, so when I give that x its own log, it is going to be added. The y is divided. There's a quotient between the 4 and the y, so when I give that y its own log, it is going to be subtracted. Number 7, I have 3 values as well. I have a 5, an x, and a y. So I'm going to start, this is going to be a two-stepper, by giving each one of those values their own log. So I have log base 3 of 5. X squared was multiplied by 5. So when I give it its own log, I'm going to add the 2. And my last one, y cubed, was also a product or multiplication. So I'm going to add that as well. Now, I know I'm done when I have used all of these properties. And if you see where I have not applied that power property. So anywhere that I have an exponent in my argument, so for example, here my squared and my cubed, I need to get rid of that. And I'm going to get rid of that by bringing those exponents in front as coefficients. All right, so I have log base 3 of 5 plus 2 times log base 3 of x plus 3 times log base 3 of y. So again, each of those terms, the 5, the x squared, and the y cubed, each got their own log, and then I brought those exponents in front. All right, last one. I still have 3 things. I have an x, a y, and a z. There is no base written, so again, I know that's a log base 10 or a common log. Let's start by giving each one of those values their own log. Starting with the x squared. Now, how do the other two compare? That y, the square root of y and the z squared are in the denominator. So since the square root of y is in the denominator, I'm going to subtract the log of square root of y. The z square is also in the denominator. So again, I'm going to subtract the log. So I have minus log base 10 of z to the second. Now, I don't like that I have exponents to those arguments. However, I'm going to write one more step here before I bring them in front. Log base 10 of x squared minus log base 10. This square root is actually a 1/2 exponent minus the log base 10 of z to the second. So one more thing, using that power property, each one of these exponents needs to go in front as a coefficient. So I'm going to move the 2, the 1/2, and the z. So let's finish this off. 2 log base 10 of x minus 1/2 log base 10 of y minus 2 log base 10 of z. And I'm done. Okay, we're going to look at one more example. But before we do that, let's rewrite these properties one more time. If you have a product in the argument, when you give each of those values its own log, you are going to add them together. When you have a quotient in the argument, again, you're going to give each of those values their own log, but you are going to subtract them. And the power property means I'm going to take that exponent for the argument and I'm going to put it in the front as a coefficient. Okay, you are asked to evaluate 3 different expressions, and each of those cannot be done in your calculator because the base is x. So what I'm going to do is I'm going to use these given values to evaluate these expressions. However, if I look at my arguments, I have a 10. Well, I don't see that here. I have a 2 and a 3 and a 5. I have a 30. Again, not one of the arguments that is given. And 6 over 25. Holy cow. Well, let's think about how I can rewrite these arguments. Well, I know that 10 is actually what? Well, it's actually 2 times 5. So if 10 is equal to the product 2 times 5, I know that if I have a product in my argument, I can use that product property and I can give each of those numbers its own log. So log base x of 2, I'm going to add, because of the product, log base x of 5. And now I can make a substitution. Well, log base x of 2, I know is equal to 0.3562. And log base x of 5 is equal to 0.8271. So let's add those numbers together. If I have 0.3562 and I am adding 0.8271, that gives me 1.1833. Let's try that same logic, or apply that same logic to this one. Now I have a 30. How can I break the 30 up into a 2, a 3, and a 5? Well, 30 is actually a product of all three of those. If you think about it, 2 times 3 gives me 6, and 6 times 5 is 30. So I can expand that 30 into the product of log base x of 2 times 3 times 5. Since there is a product for the argument, I can break that up and give each one of those values its own log. Log base x of 2, again, I'm adding because it's multiplication. I'm now going to make a substitution with those decimals that I was given. Log base x of 2 is 0.3562. Log base x of 3 is 0.5646. And log base x of 5 is 0.8271. Let's add those together. So 0.3562 plus 0.5646 plus 0.8271. And that's going to give me 1.7479. Okay, one more thing to try. And the numbers are getting larger and larger and larger. So let's look at this last one. The 6 divided by 25. Well, that's going to be pretty complicated here. How am I possibly going to get that 6? Well, I know 6 is actually 2 times 3. And I can think about the 25 two different ways. I can think about it as 5 times 5, or I can think about it as 5 squared. Let's look at it with the exponent there. All of the logs, when I expand them, are going to build off that first argument. They're going to build off that 2. So I have log base x of 2. The 2 and the 3 were multiplied, so I'm going to connect those logs by addition. The 2 and the 5 squared, that's a division or a quotient, so I'm going to subtract that log base x of 5 squared. Now, I chose that just so we can look at something a little different. If you can see, I have the power property there. This 2, I can move in front as a coefficient. Now, if I don't want to do that, I could have written that as 5 times 5. That would have been fine as well. So this is going to give me log base x of 2. So 0.3562. Let's add log base x of 3. 0.5646. And when I bring that 2 in the front, I'm just going to keep it in yellow. I'm going to multiply that by whatever I get for my log base x of 5. Log base x of 5 is 0.8271. This is a tough one. All right, so I'm going to take my 0.3562 and I'm going to add 0.5646. Now, from that, I'm going to subtract 2 times 0.8271. 0.8271. All right, and that's going to give me negative 0.7334.